and take a test function which is supported on a tubular neighborhood from the beginning, from is a globally hyperbolic space-time region.
Okay.
In a tubular neighborhood, I take a test function.
Here's a globally hyperbolic region. Now, what do you want?
That's fine. Okay. I take a tubular neighborhood and
Of
go
this, you
from
mean?
The entire thing?
You mean
some
like
tiny-
this, something like this?
no, from the
Neighborhood of a curve, you mean? I'm not sure what you
take
Sure.
take a line from one boundary to another.
Oh,
and then
this?
stick it.
Path, a trajectory.
You can take this whole
You can go to
region.
the interior.
Take the whole region, okay.
No, I don't want. Just a,
I think he
just
wants
a
a whirl line.
Just a
You want a
Thicken.
whirl line, a tubular region around a whirl line?
whirl line is a. It's like a. It is a.
You want,
Is
you
it
want a
path?
region
It's
that
not
looks
a-
something
it's
like
just a-
this?
Just a path like in a path in the.
Yeah, like
Yeah,
this.
but
yeah,
thicken
path.
it. But thicken it.
Yes,
Yeah,
yeah.
yeah, yeah. So tubular neighborhood about a whirl
Path,
line.
any path. Take a test function supported there.
Yes,
Take a quantum field and average it on that.
yes.
Then its expectation value is given by the quantum field theory. If you take a state,
Yes.
it looks to me like this assignment of probability is something like that.
The exact relation between that
No.
and the path integral is complicated because there's this time ordering issue, right? So if you write something as a function of, as you've done here, of the, well, you just took an average, so then it's probably okay, because the time ordering doesn't come in, you haven't multiplied any field. Never, I'm just thinking out loud, so. Yeah, so in that case, it would be given by.
It looks to me very similar to.
I mean,
Yes,
it's a
that's-
question of whether you, how you define your
But-
cylinder sets or whatever.
But I haven't talked about that, I've talked about just measures of events. Now you're talking about something that's analogous to
I
expectation
said this is an
value.
event in your language.
No, it's not an event. The event, what is the event?
Any one which does not exist, you need a collection, no, a line.
So you want some test function here, and you want me to form
So is
a
the
variable
event,
which is like the
is the event
integral
where
of
the path lies
I
in
of
this region?
x.
I don't know a path, but I
No,
think
but
that
the event has to be on a
I know the
specific
definitions
space.
are not the same. What I mean is this seems to correspond to that. The notion
Roughly
of a path
speaking-
does not exist in the quantum field theory. In a,
Yeah, so here I,
because
here.
different localized fields on a line.
Yes, yeah, that's right. So I'm doing,
In a quantum field
I'm
theory,
cheating here, I'm idealizing the photon as just a point particle, which it really
Sorry?
can't. I'm not doing the full QED of this thing, I'm just idealizing the photon as if it were a point particle, which it really isn't. And so that's all being ignored, so is that what you're talking about? Are you asking how I would actually justify this from the point of view of?
no, I am saying that there may be an analogous set of equations in standard quantum field theory, which seems to me, at this moment at least, to share the eventual results of what you're doing.
Well, some
The
things.
individual definitions may not match.
Here's an in principle, since it's just a since mathematics is at some level interchangeable, you ought to be able to compute these quantum measure. You ought to be able to embed it somehow in the ordinary quantum field theory.
For example, it would be the current of a
But
charged particle stays near on a tubular neighborhood. So it will be telling whether the particle, what is the probability of the particle going through that tubular
I
neighborhood.
think what,
Yeah,
what
we-
you want
we
is, I think what you want is like essentially getting quantum mechanics first as a system of trajectories in terms of quantum
it's not
field
as
theory.
simple as you're saying.
Quantum field theory
But
or
the
could
same
be
questions that can be
charge
asked
the
there.
currents. What I mean is,
Okay.
Maybe we
let-
should-
let
I think it's the same
Rafa-
thing.
I mean, okay, so do you think?
I just want to do this. It'll just take 2 minutes to do this, then we can break.
So we leave the questions to when Rafael can finish this.
Yeah, I mean, let's say that questions that have to do with connecting this up with another formalism are postponed until at least I finish describing this formalism. 'Cause the answers will be more obscure before that. So let's look at one other event, which I call, which one did I do? 8. So E8. So now there'll be, I won't bother with the pink and so on, but gamma 1 will now be 1, 2, 4, 8, and gamma 2 will be 1, 3, 4, 8. There's always really only 2 choices. It reaches 8 going this way above or going by the lower path. Okay. In the first one, 1, 2, 4, 8, what happens? It propagates, it goes through amplitude 1, it bounces off amplitude I, it bounces off again amplitude I, so that has an amplitude of I squared, which is -1. On the other hand, amplitude going the other way, it bounces off amplitude I, bounces off again amplitude I, passes through amplitude 1, so again it's just in a different order, but it's I squared, so it's again -1. So in this case the net amplitude is -2, and if you were to not worry about normalization and square it, you'd get 4. So the main thing is that in this case the measure of E8 is not equal to 0. It's positive. It always, obviously by the way it's constructed, it'll always be positive if it's not 0. It can, there's nothing in general that'll force it to be between 0 and 1. It's important to note that, but it's positive. And so in this case, it means that E8 is not precluded, and that means that E can happen. And in this particular case, that event can happen. In this particular case, we can go further using the Born rule and saying that that gives us a measure of how often this detector would fire. So that's a kind of review, of just setting up. And now I guess we should break before. The next thing I want to do, which may be the last thing, I don't know exactly, I don't know how to do this, but I want to do the same thing, embed this in a slightly more complicated arrangement of mirrors that shows the paradoxical nature of quantum mechanics.
I was just wondering, you could put
I think
mirrors
Sorry,
and
Sabi,
You didn't see behind you.
Sorry,
non-quantum.
before you erase this example, so any which way you would have permuted the i's and the 1, you would have got the same amplitude at the end because you are multiplying 3 of them.
Yes, that's
And
right.
this is what comes to the question that Anjan was asking, which is, how does it know that it's going down a particular path? Well, the point is, this is permutation. For this specific example, it is permutation independent. And that brings me to the question that I want to ask is there a time ordering that we need to follow when we are taking into account this example?
Well, that's a very good question. Yes. So in this class of examples, there is not. I mean, time is there just because these are trajectories in space-time, although I didn't draw the temporal aspects. But there's nothing, the time ordering is not playing any crucial role. That's related to the fact that quantum mechanics standard model is CPT invariant. It doesn't distinguish a direction of time.
It's not. It can also be the argument for non-locality.
Yes, so that's right. There's a lot of deep issues come in when you ask about time ordering. My feeling is that the real theory, the time ordering is crucial. In here, as you said, it doesn't matter. You're just multiplying the amplitudes together. But I think the general situation is that what can happen in the future depends on what has happened in the past. And I can't give a very simple answer, but I want to stress that that's an important question.
I mean, it's also important that it's a unitary system. So
Also unitary.
Actually,
It's not
beam splitter is not
unitary,
unitary. That's the other.
Which is not?
Unitary
A
is
beam
not
splitter is
necessarily
not
related.
unitary
It's not?
because you have to consider the fourth port,
Oh,
which is
yes,
the
yes.
vacuum fluctuation,
Oh.
and there it sort of breaks away from
So
unitarity.
explain this.
Oh, this is
Yes.
going beyond the one photon approximation.
No.
No?
Irrespective, the whole point of the beam splitter is that it has four ports: 1, 2, 3, and 4.
Yes.
And obviously, when you're coming incident on a beam splitter, you go one way or you go the other way. But there is this emptiness here, and that is the vacuum fluctuation, which, if you do QED, that decides. That arbitrary stochasticity decides which is the direction that the photon is going to take. That is the formal way of treating a beam splitter. So the point being that if you construct a Y junction where you have one input and two outputs, this is not the same
that cannot,
as a beam splitter as described, as used in the Mach-Zehnder.
But for massive particles,
So
Massive
there is
part-
a huge controversy
well,
about.
so the massive. So, for example, his example, I don't think depends on being photons. One can
no, it
consider
doesn't,
neutrons,
it doesn't.
neutrons, beam splitters. So then, this
Yeah, but
kind of
there's a
question-
huge controversy
Yeah, I know.
about atom interferometry for precisely this reason, because people wanted to make a Mach-Zehnder interferometer for gravimetry to detect phase change in the gravitational field. And what you do is you make a Y junction. You have a guide, you make a Y junction, and then you recombine in another inverse Y junction. And that's supposed to be an interferometer. And when this first was proposed, there was a massive outcry.
Because of unitarity.
Exactly, because that's not a beam splitter.
Well, yeah, I mean, I'm not quite
but
understanding.
there is a controversy because, for example, for all the neutron interferometric experiments I know of with this beam splitter Mach-Zehnder, they don't bother. The experimental results are consistent with not
So but
considering it.
So there is some
unitarity.
deep stuff there
So-
which
so
we don't
it-
know.
it's not-
What
So for your example to work, I
I
think
think this is a
for
simplified
neutrons.
version, which everything is unitary, right?
Or maybe
As
it
far as
was
I can see, it's in the
expected
mathematical
for
sense, it
neutrons.
is unitary. So I'm not quite sure. You'll have to explain to us at some
Yeah,
point.
we-
Well, yes,
we
it
discuss
is-
all this stuff.
it is a very critical point. I know, and
But unitarity comes in fundamentally in measurements.
So what about linear optics quantum computation?
There's one more question.
Sorry?
Such
No, I was
Oh,
just going
such
to
a-
say that if you put a partially reflecting mirror perpendicular to any one of the beams, then with the probability of some probability P for transmission and whatnot, I mean that would give us that would not that would make the calculation much more complicated, right?
Well, it would make it more complicated. Yeah, then it could bounce
And
back
it
and
would,
forth, and then you could get an sort of,
and it
you
would-
get an infinite
then it
number of
would,
histories now.
And it could also, I mean, I can't justify this, but it could also introduce questions of time ordering because in one path you would go through the partially reflecting mirror and the other path you wouldn't.
Well, this is, but these are kind of partially reflecting mirrors.
No, I
Aside
meant
from the fact that it's,
no, I
the
mean
angle of it-
perpendicular to the beam of the.
yeah, I understand, but why is that, what's essentially different about having it perpendicular rather than?
Because then there is a problem. In this case, the beam never goes back.
But it's not so much the back and forth as the fact that
No.
simply the number of times, it doesn't matter how that set is ordered. Because you're just multiplying amplitudes.
It's not going back in space-time, of course.
No,
It's
of
going
course.
back, it's always going forward.
Yeah.
So Urvashi,
Yeah, so I was just saying that in LOQC, that is linear optics quantum computation, we say that every unitary operation in SU2 can be written in terms of a beam splitter and a phase shift. So I have to understand this better, Sadiq. This thing about the beam splitter not being unitary, because what is going wrong here? Because in LOQC that's what we do, right? That everything is written in terms of a beam splitter matrix and a phase shifter. And all SU2s can be broken up as products of these.
And the phase shift is just that propagator that I
Yeah,
didn't.
exactly, which you
make
did not
explicit.
comment. So that's exactly what you're doing here. So everything can be written in terms of a Mach-Zehnder interferometer in
The phase
qubit
shift.
space.
The phase shift.
Yeah.
Is it a random phase shift or is it a
It can be anything. No, it's not just the pi phase. It could be anything.
So maybe that's where the problem comes. I mean, look, it's not that I have the theoretical explanation at the top of my head, but the point is that when in quantum optics, when you're talking about the beam splitter, you are always, and you're doing a formal calculation, you are always considering the vacuum port.
But then, does that necessarily mean that it's non-unitary? That's the question. Because then everything would fail.
It's a fluctuating.
Well, but you're doing quantum field theory, aren't you? Now, by the vacuum part,
Yeah.
maybe you mean that there could be a fluctuation coming from here, which I didn't take
Yes.
Right.
into account. So that's saying there's a mode associated with this. It could be empty, it could be filled, it could have occupation number 1, it could have
It has a
occupation
variance.
number 2. So that's, yeah, so I mean, you're doing real quantum field theory now. So
Yeah.
this is just an idealized situation where we,
I agree.
And in this, I think the mathematical, I think that it is unitary. I think this transfer matrix, or whatever you want to call it, this amplitude associated with
So my question was related to the time ordering and
I see.
which was a different thing.
I was saying, does the need to take into account this vacuum port
Yeah, I don't know.
force us into taking time ordering more serious?
The time ordering
I'll have
was.
to say, I don't have an answer off the top of my head. Maybe.
Yeah, I was just going to comment that if you want to make it non-commutative, all you need, in the sense that the order of the operations matters, all you need to do is to have polarized values, and you have the transfer matrix, which is a real matrix, and not just a phase.
Yes, that's true. Yes, that's true. Yeah. If it's that's right.
Then you won't need phase. Then you won't need
But
phase.
At the end of it, you will have.
Well, let's see. I'm not sure though. I mean, if you'd have to. I mean, it's always going to be a phase because the individual, unless we go to some general, it's true that spin raises some issues. If we
The phase.
I purposely ignored spin because it just complicates the story from the mathematical point of view. So maybe that by including spin you wouldn't get something non-commutative. One way of including spin is by letting the amplitudes be operators and be SU2 operators. And that is true. On the other hand, if I introduced another variable to represent the polarization and treated it as part of the reality, then I'd be back to the single complex number.
So just quickly, we need to anyway wait for tea because there is no tea outside.
Oh.
Somehow they gave us tea at 2 o'clock and they didn't realize we also need tea at 3:30. So I'm trying to make sure that some kind of
Okay.
I just have a question on whether, they have these which way detector kind of experiments where if you put a detector there, then you do not see interference. So in describing an
Yes.
experiment of that sort, in this formalism, would you say that the event E8 is modified and we have the
Yes,
E8
if you put a detector present,
in one of the
yeah, so
parts?
that's a crucial. If you put a detector at the end, it doesn't matter really. This particle is its own detector. The fact that it emerges in a, we can say that is the detector. Of course, it wouldn't be that you could, unless you were the photon, you wouldn't be able to be aware of this detection yourself. But on the other hand, if you put a detector, say you put something here, that of course modifies the subsequent behavior of the particle. And so then you'd have to reanalyze this whole thing with the detector explicitly included as part of the physical setup.
That would be a
And
different
that which way, yeah. That when you reanalyze it with the detector taken explicitly into account, then you would see that things that might have interfered no longer interfere. Basically because the detector, again, the detector could be modeled as something very simple. Unfortunately, you don't want to model a realistic detector because it's got 10 to the 23 atoms and various things like that. It could be something very simple. It just throws a switch or something like that. And then you would see that if you detected where it was, you'd end up with a switch. If this detector did find it, the switch would be one way. If you didn't find it, the switch would be the other way. Those would be different final states, final configurations, and that relates to the question that Paul asked. Different final outcomes, as you might call them, don't interfere with each other. That's what cancels that's why the interference goes away when you find which way.
Now we do have time for questions.
So we just cancel, I guess we'll just give up on the rest. I don't see how you can say anything in a minute.
Okay, why don't you just, is it okay? I mean, and maybe there's water
How
outside,
many
we
people
could
are
have a
outside?
drink of water and then come back.
Is there a cutoff time when you stop here?
There's no, I mean, it would be Raman getting tired and us getting tired, I suppose. Not for me, so.
We need Red Bull.
But
I need some advice. So